physics community had run into paradox. Let's try to clearly elucidate what that paradox is. Newton's laws appear to be consistent with the dictionary of Galilean relativity. Maxwell's equations appear to show an inconsistency with Galilean relativity. Firstly, because there was a constant c, which indicates that light has to travel at a fixed speed with respect to something, and we need to know what that something is. And it was speculated that this was because of ether, but the null result of the Michelson-Morley experiment told us that there appears to be no ether. Okay. So, what are the possibilities now that we could imagine to resolve this discrepancy? Well, the original possibility of reconciling Maxwell's equations with Newton's laws was to speculate that there's an ether and therefore there's a preferred rest frame, but this was ruled out by the null result of the Michelson-Morley experiment. A second possibility is maybe Maxwell's equations are just wrong. Okay, and maybe they have to be modified to correctly fit with the Galilean relativity principle. Or a third possibility is that maybe Galilean relativity is wrong, and there is a new relativity principle that describes how different observers translate their observations between each other. And this new relativity principle is consistent with Maxwell's equations. Now, if Galilean relativity was wrong, that would also imply that Newton's laws are not correct. Okay, so this would also imply Newton's laws are incorrect or need to be modified because they fit quite well with Galilean relativity, or they appear to. So the question is, if you take this third approach, is there perhaps a new relativity principle that is consistent with Maxwell's equations and modifies the form of Newton's laws so as to also be consistent with this new relativity principle? And therefore, the original form of Newton's laws, which is consistent with Galilean relativity, is wrong. Although it was hard to imagine at the time how this could even be possible. It wasn't until the year 1905 that a young patent officer in Bern in Switzerland named Albert Einstein, who was all of 26 years old, began to think deeply about the idea of the Michelson-Morley experiment and came up with the new relativity principle, which was dubbed special relativity. We will see Einstein's reasoning and we will follow it to understand exactly how he came up with this new relativity principle and the simplicity of thinking that led to it. If you're going to abandon Newton's laws and treasured principles of Galilean relativity, you need to know what ground you have to stand on. If you can't trust anything, where do you begin? And we will see that the genius of Einstein was to figure out what are the right principles, what are the right things, ingredients to begin with, to assume in the character of the physical law from which he derived his new relativity principle. So Einstein tried to figure out what are just the bare minimal building blocks that he needed to characterize what different observers would see and what the nature of physical laws really was. And he made a few simple postulates. So let's write those down. These are the postulates of his new relativity principle called special relativity. So the first thing he did was to assume that there are still a class of observers in this new relativity principle whom he called inertial observers, or they inhabit what are called inertial reference frames. And his first postulate was that whatever the laws of physics, whether Newton's laws, Maxwell's laws, these laws of physics are the same in all inertial reference frames. Okay? That is, there are a class of observers who are in a state of constant relative motion to each other, and these observers should all see the same form of the physical laws. They might differ again in their descriptions of the physical laws, of various quantities like positions and times, but they will agree on the form of the physical law. Okay, that was a starting point. Then he took a second principle, and this was where he differed with what had come before from Newton's laws. He simply took it as a principle of nature that the speed of light c is a constant in all inertial reference frames. This would obviously explain the null result of the Michelson-Morley experiment, because if the speed of light c was the same for all inertial observers, we would not be able to detect any fringe shift in the Michelson-Morley experiment. Because no matter which direction you look, the speed of light was always going to be c. And therefore the phase difference between two arms of an interferometer would not change if the light was traveling in different directions. Now, in addition to these two postulates, there are a few unstated postulates which he invokes at a later time. So these are the so-called unstated postulates of special relativity. But these are also very simple, which is to assume, one, that there is an origin independence in space and time. That is, there's no preferred position in space and no preferred position in time. Okay, so this is called the principle of homogeneity. All points in space in a given reference frame appear to be equivalent. Right? There's no difference between here and there, or between now and in the future, the form of the physical law stays the same. There's no preferred point in space, and there's no preferred point in time. So this is called the principle of homogeneity. And the second unstated postulate is to assume isotropy, which means if I rotate my coordinate axis in trying to describe my system, again, I should see no change in the character of the physical law. Okay? That is, my physical law doesn't care about which direction I refer to as the x-axis, the y-axis, and the z-axis. Even if I rotate these axes so that perhaps the x-axis is pointing here, the y-axis is still pointing this way into the paper, and the z-axis is pointing this way. Even under this rotation, the physical law would take exactly the same form. Okay, so homogeneity has to do with translations in space and time. Okay, this is where you're talking about observers who are not moving with respect to each other, but are just located, have different choices of their origins in space and time. And isotropy has to do with observers who have axes which are rotated with respect to each other. And all such observers should again measure the same form of the physical law. And he simply began with these four principles, no other assumptions, and he used these to derive a new principle of relativity. So let's summarize these principles again. One is the principle that there are a class of observers who inhabit inertial reference frames, and the laws of physics must appear to be the same for all these observers. Second, the speed of light c is a constant in all these inertial reference frames. Third is the principle of spatial homogeneity, or the fact that no point in space and no point in time is special. And the fourth principle is the principle of isotropy, which is there's no preferred direction in space. So there's a rotational symmetry of the laws of physics.